This is a planet in formation in a very distant region of the solar system, both in space and time, when the center of the Milky Way was much more active than it is today. Massive stars are ceasing to exist, expelling various elements generated in their cores, and one of them is gold. These elements will embark on a journey of millions to billions of years before reaching Earth. Curiously, these same elements will still remain on Earth even after the last human gives up. In addition to gold, there are elements with even more exotic origins, found in even more hostile and distant places. If someone were to observe them in their place of origin, they might swear they are part of an alien universe, the Strange Mother. Today, we will delve a bit more into the origin of these elements and how still unknown elements, originating from distant worlds in the universe, may be closer than we imagine. Since we mentioned gold, let's start our list with it. As this precious metal can only be created under extraordinary astronomical conditions, unlike many elements, it is a rather rare metal. So much so that over millennia, with all the gold extracted around the world, it is estimated that only 200,000 tons of this precious material have been unearthed so far. Despite seeming quite substantial, this amount is enough to form a cube with 22 meters on each side, and today it is believed that there are only another 50 tons underground, with most of this quantity being around the planet's core, completely out of our reach. Now you might be wondering if we produce diamonds and many other things artificially. Gold can be made just as easily. To make gold, a process called transmutation is required, which involves transforming one element into another through nuclear reactions. This can be done in particle accelerators, nuclear reactors, or atomic explosions. However, as we can see, this requires a lot of energy, sophisticated equipment, and specific conditions. Currently, this process is very expensive and inefficient, as it produces only a small quantity, and as a consequence, generates radiation in nuclear waste, which is neither advantageous nor practical. Thus, it is much easier and cheaper to use what is found in nature. Another element that is quite common, in fact, is the fourth most common element on Earth, but it is not easily found pure in nature: iron. It is usually mixed with other elements, forming iron ores used to make many things we use, such as bridges, cars, pots, and refrigerators. Iron is very important for humanity, as it can be transformed into different forms and alloys, such as steel, which is stronger and more durable. This material was also created a long time ago, before our planet existed, formed in the cores of very large and hot stars that later exploded in supernovas. These explosions scattered this and other elements throughout space, which later came together to form planets, moons, asteroids, and everything else. Therefore, it is present in many places in the universe. Another element that is quite abundant is carbon, a type of atom that can join with other atoms and form different substances. It is present in virtually everything we see, from plants, animals, rocks, plastics, and even you and me. Carbon is commonly produced in stars with low and medium mass, those that have between 0.5 and 10 times the mass of the Sun. When these stars age, they release it into space, along with some of their gas, and also through stellar winds or explosions from planetary nebulae. There are even records made by telescopes of some stars generating this carbon and releasing it into space. Unlike gold, carbon can be produced artificially using machines and chemical reactions. Currently, there are different forms of using it. For example, graphite is black and soft, diamond is transparent and hard, coal is dark and combustible, and so on. Some forms of carbon are easier to produce than others, depending on what is needed, what is available, and how much is spent. Many elements observed in the universe can also be produced on Earth. However, like gold, some become so difficult to create that manufacturing them is an impractical task, and consequently, they are limited on the planet. Some of these elements are even limited when we consider the entire Milky Way, but perhaps the most contradictory aspect lies in helium, a noble gas that can only be found in small quantities in the atmosphere or in some natural gases. It is used in dirigibles, refrigeration, medicine, and other areas. This gas was produced in large quantities in the early universe. However, the fact that helium was formed in the Big Bang does not mean that it is abundant on Earth. This is because helium is a very light gas that does not combine with other elements and does not dissolve in water, allowing it to escape Earth's gravity. Helium present in the Earth's atmosphere eventually escapes into space over time, while the helium inside the planet tends to be trapped in rocks or minerals. Additionally, Earth received very little helium from space as it was swept away by solar wind during the formation of the solar system, making it rare on Earth but abundant in the universe. It can be produced by nuclear reactors or particle accelerators, but this is very difficult and economically impractical. Another scarce element on Earth is lithium, an alkali metal widely used in batteries, medicines, and other applications. It was formed in the first minutes after the Big Bang and is also created by low-mass stars in their outer layers. It can also be generated by gamma-ray bursts, highly energetic phenomena that occur when two neutron stars with a black hole and a neutron star merge. Lithium can be extracted from some minerals or salty water, but currently this requires a lot of energy and resources. Moving on to another item on our list, we arrive at uranium, one of the heaviest elements on the periodic table. This element is used as nuclear fuel in reactors and weapons. It is formed by Type II supernovas, which occur when a very massive star collapses and explodes. In this event, the iron nuclei present in the core of the star capture neutrons and transform into heavier elements, such as uranium. Today, many countries can enrich uranium to generate energy in nuclear reactions, making it important for civilian and military use. Depending on the level of enrichment, it can also be used as material for atomic bombs. However, this involves significant risks, including security, control, and cost, which is why this work is regulated by international agreements. In nature, uranium can indeed be found in some ores, but its extraction and enrichment also involve expensive and quite dangerous processes. Another element that also emerges in Type II supernovas is copper, an orange-red metal with many applications in industry and technology. It can be found in nature in various minerals, and its artificial production is very complex and expensive, not worth it from a commercial standpoint. As for silver, the precious metal used in jewelry, cutlery, mirrors, photographs, and other items, it is formed in large quantities during the collision events of a type of star that came very close to becoming a black hole, becoming so dense. These neutron stars mentioned earlier, along with silver, gold, lead, and niobium, are also mostly formed in the collision events of these stars. These events generate the most powerful explosions in the universe. In these collisions, in addition to generating bursts of gamma rays, a form of high-energy electromagnetic radiation, they eject particles moving at speeds close to the speed of light and also create turbulent environments sufficient to forge elements like silver. These elements are then dispersed through space and can be incorporated into other celestial objects such as planets, asteroids, and meteorites. Perhaps the biggest surprise is related to niobium, a metal used in superconductor alloys, aerospace applications, and more. It is abundant in Brazil, but its exploration is controlled for strategic and geopolitical reasons. It can be artificially created on Earth. But like some elements mentioned earlier, the limitation to produce it involves the lack of technology and sufficient energy to reproduce these processes, as well as the generation of nuclear waste. On the periodic table, all naturally occurring elements found in nature have atomic numbers up to 98, which is the atomic number of californium. There are also artificially generated elements with atomic numbers above 98 up to 118, created in laboratories under extreme conditions. These elements are typically very unstable and decay rapidly, within seconds or even less. However, in the universe, the hypothesis that these elements between 98 and 118 may be found in large quantities without decaying is raised, and many researchers go even further, believing that elements beyond 118 may exist. For some time, there has been suspicion that some asteroids in the solar system may be hiding even denser elements, possibly more than the unstable and radioactive ones with atomic numbers between 105 and 118. It is suspected that some of these asteroids may contain super-heavy elements, not listed on the periodic table, made possible by unknown processes that generate these elements in a stable form. Among these processes is the interaction between high-mass and high-metallicity binary stars, the most common type of stellar system in the universe, about which we have little knowledge of their environments and nearby regions. Binary stars are systems of two stars orbiting each other. They are quite common and can have characteristics quite different from those observed in the solar system. High-mass binary stars among them have a composition with heavier elements than hydrogen and helium in greater quantities than the Sun. These stars, often brighter, hotter, and bluer, undergo faster evolution and can produce many more heavy elements. The researchers' hypothesis is that the interaction between these binary stars could generate extreme conditions of temperature, pressure, radiation, and magnetic field, favoring the formation of these elements not present in the periodic table, far beyond the 118 that we know. These superheavy elements would then be incorporated into some metallic asteroids, giving them a much higher density than expected when measured with our telescopes. An example is the asteroid 33 Pomyeia, located in the asteroid belt between the orbits of Mars and Jupiter, with a diameter of about 50 to 60 kilometers and a density of 75.2 gralen per cm3, much higher than that of osmium, the densest natural metal we know, with a density of 22.59 gram per cm3. This means that asteroid 33 Pomyeia has a density 3.3 times higher than that of osmium. This difference is considerably large and difficult to explain solely by the metallic composition of the asteroid. For this reason, some researchers suggest that it may contain super-heavy elements not present in the periodic table. The 16 Psyche, another asteroid located in the belt between Mars and Jupiter, with a diameter of at least 226 kilometers, believed to be the remnant of the core of an extinct planet resulting from a violent collision in the early solar system, has also shown indications of carrying metals beyond the periodic table. If this is true, we may soon obtain more answers, as the mission to 16 Psyche was launched by NASA and SpaceX on October 13, 2023. The probe is expected to reach the asteroid in 2026 after a 4-year journey through space, with the goal of studying the origin, structure, and composition of this asteroid, estimated to be worth more than the global economy of Earth. I hope you enjoyed it. Don't forget to share your thoughts on the topic in the comments. If you're not part of our community yet, remember to hit the like button and subscribe. It's crucial for the channel to gain visibility, which in turn helps us create more content like this. Thanks a lot. See you next week.